Alright, y'all, I got another phase line video for you. So we're going to find all the critical points, inflection points. We're going to graph the phase line of this function right here. Y prime equals y squared times 4 minus y squared. So we know that the critical points this time are a little bit easier. It's when y prime equals 0. You remember that dy over dt is the same thing as y prime. They're just different notations. So we can see that y prime is 0, or dy over dt is 0, at y equals 0, right? Because when you plug in 0 here, the whole thing's going to go to 0. So y equals 0, and then we have y equals plus or minus 2, because when you plug in 2 there, this whole thing will, this part will turn to 0, which will cancel out anything. So y equals plus or minus 2. So let's do our increasing and decreasing test. And we can see that, so 0, -2, +2. So now let's start plugging in points that are in those intervals. So we'll start with -2, any point between negative infinity and -2. So we'll do -3. So -3 squared is going to give you 4 minus 9, right? Which is going to give you a negative value, and then this is going to give you positive 9, so negative times a positive is a negative, so it's going to be decreasing from negative infinity to -2. Now we'll try -1. -1, this will be positive, positive, so this is positive. 1 is going to give us the same value, right? Positives. And then after 2, we're going to get negatives again. 3, it's going to be the same story, so negative. So decreasing, increasing, increasing, decreasing. Now I'm going to erase this, and we're going to test for inflection points now by taking the second derivative of this function. So let's go ahead and set it up. Y prime equals, I'm going to go ahead and distribute this y squared out. It's a little bit easier. You could use a chain rule if you want, but it's just a little bit easier for me to do it this way. 4y squared minus y to the 4th power. Now let's take the derivative of this to get y double prime. So y double prime equals, that's going to be 8. Actually, this works a little better. This is going to be 8y prime, right? 'Cause the chain rule. This is implicit differentiation. Minus 4y cubed y prime. And now we can factor out the y prime. And we can also factor out a 4, right? So let's factor out a 4, the coefficient, a y, and then also y prime. So we'll say 4y, y prime, right? Multiplied by, well, this is going to be 2, and then this is going to be minus y squared. 2 minus y squared. Right. Okay. So I believe that's correct. Y prime and -4 y cubed y prime. Yep. Okay. So, and we know what y prime is equal to. Y prime is this. So let's just plug that in. So y double prime equals 4y, and then multiplied by y squared, 4 minus y squared, right? And then this function right here, 2 minus y squared. Okay? So what I'm going to do is I'm going to erase this, and I'm going to keep working on this part a bit further up here. I don't think I need any of that. Nope. Okay. So, and we always want to use, when we plug y prime in, when we plug y prime back in, we always want to use the most simplified version of y prime we can, because it's easier to see where the zeros are going to be when it's simplified. That's like a really big point of simplification, is so you can see the zeros easily. So now let's see where all of our zeros are with this function, right? So we're going to need this. I'm going to go ahead and copy it right up here. I'm going to go ahead and make this a y cubed. I'm pulling this y squared out. Y squared and 2 minus y squared. Okay, so let's find the zeros of this, and this will give us, the zeros of the second derivative will give us our inflection points. So, we know that y equals 0 is one of them, y equals plus or minus 2 for this, right? And then y equals plus or minus root 2 for this one. So plus or minus 2, y equals plus or minus root 2. Okay. So now let's test it, right? So what we're going to do is we're going to draw this number line. I find this is the easiest way, the most efficient way if you just take the time to write it out. You're not sitting there like plugging it in your head and taking this and copying it somewhere, or just leaving it there and then like going down and drawing the phase line. So we have 0, negative root 2, positive root 2, 2, and negative 2. So now let's start plugging stuff in, right? So we've got, yeah, okay. So before negative 2, let's just plug in negative 3, right? And then we will go ahead and erase these so I can put the signs where I'd like them to go. Okay, so before negative 2, let's put in negative 3. So this is going to be negative, right? So negative 3, this is going to be negative again, and then this is also going to be negative. So this is going to be negative and concave down. So if you remember from the last video, I said that if the second derivative is positive, you have a local min, which is concave up. And then if it's negative, you have a local max, which is concave down. Great, okay. So now we're going to go between negative 2 and negative root 2. I should have that number memorized. I think it's like negative 1.4 or something. Yeah, negative 1.4. Okay, so let's do just a negative 1.5, I guess. Negative 1.5 for that is going to give us, so negative 1.5 here, we'll start plugging it in with the calculator. So negative 1.5, this is going to be negative no matter what, right? Because any negative cubed is going to yield a negative. So let's do negative 1.5 squared. So 4 minus 2.25, so that's going to give us a positive right here. And then 2 minus 2.25 is going to be negative. So this is two negatives and a positive. It's going to give us a positive, right? So concave up. So now a number between 0 and negative root 2, we'll just do negative 1. I'm actually going to write down these values down here. That makes it a little more simple. Negative 1.41 and 1.41. Arrow. Okay. So now a number between 0 and negative root 2, we'll do negative 1, right? So negative 1, this is going to be negative. Negative 1, this is going to be positive, and then this time is going to be positive. So we have a negative value concave down. So now a number between 0 and root 2. We're going to do 1 this time, so now this turns positive. Positive, 4 minus 1, 2 minus 1, positive. So positive concave up. Now this is 1.41 roughly, so we'll do 1.5 again. Positive, 1.5 squared, what did I say that was? 1.5 squared is 2.25. So 4 minus 2.25, that's positive. 2 minus 2.25, this is going to be a negative this time. So we got another negative, concave down, and then 3 on. So 3 on, this is going to be negative. This is going to be negative, so 2 on, but I'm going to plug in 3. Going to be negative, negative, right? 4 minus 9, and then positive. So now this is going to be a positive and concave up. Alright. And I'm going to copy this, put it up here, and then we will start drawing the phase graph. Okay, I've got the graph set up. So now what we're going to do is, so what I did was I used all the equilibrium points from the original function, which was dy over dt equals, what was it, y squared 4 minus y squared, right? And that's where we got, where y prime is 0, right? That's our equilibrium points. Now we need to make asymptotes for our inflection points, right? To remember those, remember I said that negative root 2 is about equal to negative 1.41. Root 2 is about equal to 1.41. So let's go ahead and put those in there. So 1.4 is going to be like right around here. Negative 1.4 right around here. And I'm going to draw little dashed lines to remember that it's an inflection point, right? Just like that. Like that. Okay. So now let's go ahead and mark where is increasing, where is decreasing. So from negative 2 to infinity, it's decreasing. So we'll put it down. Just like that. 0 to, from negative 2 to 0 is going to be increasing. From 0 to 2, increasing. From 2 to infinity, decreasing. So now let's start drawing a graph, right? So now we have, let's go from the bottom, bottom up, right? So decreasing and concave down. So decreasing and concave down is going to look like this. So now between negative 2 and negative 1.41, we have concave up and increasing. Concave up, increasing. So draw this. I always try to go from left to right when I'm drawing these. It's kind of the way my brain works. If yours works right to left, which maybe it does, then feel free to draw it the other way. But just remember, increasing is by going from left to right if it's going up or down. So concave up until negative root 2, and it flips to concave down, but it's still increasing. So it is going to look like this. Now from 0 to root 2, which is, I'm going to go ahead and mark these as y equals root 2, y equals negative root 2 for that line. Okay, so from 0 to root 2, we have concave up, still increasing. So concave up, increasing. And then from root 2 to 2, it flips. Concavity, and we are concave down but still increasing. Just like that. Okay, so now from 2 to infinity, it's decreasing, and it is concave up. So decreasing and concave up is going to look like this. Right. Okay. And you're never going to have, so before I draw this, you're never going to have something like that goes and looks like it's going to run into an equilibrium point. So if it were like concave down, concave down to decreasing, it would never look like this. It would have to inflect and go this way. So there's got to be an inflection point somewhere, or you're missing something. So just remember that it's never going to go and act like it's going directly down. That's what the inflection points is. So if you are finding that, then you've either missed an inflection point or messed up somewhere. But we didn't, because it's concave up and decreasing. It's just going to look like this. Concave up, decreasing. Right. Okay. So now let's classify them as stable, unstable, and semi-stable. So we know that y equals 2. This is going to be a stable point, right? You won't always have a stable point. You won't always. It just depends. The last example we did seemed to work out perfectly. That we had an example of every. Oh, I think we have that again here. All right, so root. I'm gonna say that this, since they both converge from both sides to y equals 2. Remember, we're looking when testing for stability. You're looking at the equilibrium points. You're not looking at the inflection points. So y equals 2, since it converges to both sides, is going to be stable. Y equals 0, well, we have one that's converging to y equals 0 and one away from y equals 0. So y equals 0 is going to be semi-stable. And then, once again, we have y equals -2 being both away from y equals -2. So y equals -2 is going to be unstable. And that's it for this problem. I'm going to do one more phase line video, and we'll move on to probably like separable equations or something.